Imagine taking a standard steel gear, launching it into the vacuum of deep space, and watching it violently sweat out its own lubricants before just shattering.
Yeah, shattering like a dropped wine glass. It is a brutal environment.
It really is. So whether you are prepping for a highly technical R&D meeting or you just intensely want to know how rovers actually survive on Mars, today's deep dive is for you. We are decoding the extreme vocabulary of precision mechanical engineering.
Exactly, because when you drop machinery into deep space, or say a nuclear reactor, normal physics kind of aggressively turns against you.
Right, we're looking at a stack of technical definitions to understand how machines battle the universe's harshest environments.
Yeah, we're dealing with a vocabulary born out of absolute physical necessity, not just, standard engineering jargon.
So let's jump right in. The first hurdle a machine faces leaving Earth is the vacuum itself. Which brings us to outgassing. Now, I used to think of this like that chemical new car smell.
Oh,
But in a vacuum, without any atmospheric pressure to hold things together, it's more like a violent chemical purge, right? The greases and lubricants inside a gear literally vaporize.
They do. And those vaporized molecules, they have to go somewhere. They float outward and basically condense on the very first freezing surface they hit.
Which could be a huge problem.
Oh, catastrophic. If that surface happens to be the primary lens of a space telescope, well, those microscopic droplets just fatally fogged up a multi-billion-dollar mission.
Wow. And that is why the harmonic actuators positioning those optical instruments require heavily tested, specialized, low outgassing lubricants.
Precisely. But the vacuum isn't the only issue. Once you're out there, you also deal with the extreme cold of the shadow, which triggers cryogenic embrittlement.
Right. And this isn't just about metal getting a little stiff in the cold.
No. If we look at the underlying physics, as the temperature drops, the atoms lose their kinetic energy. The atomic slip planes inside the metal's crystal lattice essentially lock up.
So they can't move around anymore.
Exactly. Normally, when you put stress on a gear, those planes slide past each other, allowing the metal to bend and flex. But in cryogenic conditions, they can't slide. So instead of deforming elastically, the atomic bonds just snap.
That is wild. The metal literally shatters like glass under normal operating torque. That means standard steel alloys are, completely useless?
Completely useless, which is why critical components, like the incredibly thin flex splines in deep space drives, rely on very specific metallurgy.
Like what kind of metals?
You have to machine them from stainless steel 304 or specialized titanium alloys, materials that actually maintain their atomic mobility even at near absolute zero.
Okay, so the component survives the trip through the freezing vacuum, but then it lands on a surface like Mars. Now it's subjected to thermal cycling.
Right, the brutal day and night temperature swings.
Yeah, the metal expands in the midday heat and contracts in the freezing night over and over, which generates immense internal thermal stress.
It does. A reducer gear might undergo 1,000 hours of thermal cycling tests just to prove its thermal fatigue strength won't tear the material apart from the inside out.
But temperature is at least a macro threat we can measure. The one that really stands out in these specs is radiation hardening, specifically for robotics in nuclear waste zones.
Yeah, that's a huge one.
See, wait, I always understood radiation as an electronic threat. Stray particles flipping bits in computer chips. How does an invisible high-energy particle actually break a solid physical block of steel?
It's hard to wrap your head around, but high-energy radiation particles act like microscopic ballistic missiles.
Missiles? Really?
Yeah. When they bombard a metal gear, they physically smash into the metal's atoms, violently knocking them right out of their crystal lattice structure.
Oh, wow. So it's literal physical impact damage just at an atomic scale.
Exactly. And over continuous exposure, this atomic displacement causes the metal to swell, warp, or become dangerously brittle.
So radiation hardening is about preventing that.
Right. It requires very specific material selection and structural shielding to guarantee the gear won't physically degrade before its required lifespan, which is typically 5 years in a nuclear zone.
Okay, taking all these extreme hazards, the vacuum, the radiation, the corrosive atmospheres, it brings us to the ultimate defense used in manufacturing back here on Earth. Hermetic sealing.
Yes, and we're not talking about a tight plastic friction seal. This is absolutely environmental isolation.
Right. So essentially the ultimate impenetrable Tupperware seal for gears,
Mm.
locking the critical lubricants in and corrosive chemicals out.
Pretty much. For gearboxes operating inside things like chemical vapor deposition or CVD chambers, engineers use welded metal bellows.
So instead of a static rubber gasket that degrades, it's essentially a dynamically flexing metallic accordion.
That's a great analogy. It allows the mechanical drive shaft to move and transmit power while maintaining an impenetrable, continuously welded steel wall between the gears and the outside environment.
Because if that dynamic seal fails for even a second, corrosive process chemicals flood in and destroy the internal gears.
Or the internal lubricants leak out and fatally contaminate the semiconductor being manufactured inside the chamber.
Both sound like incredibly expensive disasters.
Oh, they are.
Well, looking at this entire stack of research, the real takeaway is that mechanical engineering vocabulary isn't just about making things move smoothly.
No, it's about waging a relentless physical war against the harshest environments imaginable. We are forcing materials to operate dynamically in places where the laws of thermodynamics and atomic physics dictate they should sit perfectly still.
Or just disintegrate entirely.
Exactly.
Which really leaves you with a final thought to ponder. If engineers have to go to these extreme lengths, using titanium, radiation shielding, and welded hermetic seals, just to keep a simple mechanical gear turning,
Yeah.
what does that say about the immense, almost impossible vulnerability of our own human biology when we try to step foot into those exact same frontiers?